Hello guys, Cyprien here from FEA for All. And today's video will not be exactly like my usual video where I show you a tutorial on how to do something from 0 to 10. Um, I will kind of show you how to work with mesh elements, but this will be more like a fun experiment to understand better how mesh works in FEA and how you can build your own mesh set from 0 using Python, and we'll do that in Jupyter Notebook. So I'll start with one of the classic example, which is this plate with a hole. So if you go on my blog, and you will find this post, which by the way is pretty old. I'm looking at it, 2013. God, I can't believe I wrote that long ago. Anyway, I will take this plate and I will try to create a mesh manually of this plate. Well, manually, I mean with Python functions. So it's more like a challenge I put to myself. And if in any moment you think that you can do better than me, or you have better ideas on how to do this, please be my guest. Just post a comment or anything, and I'll have a look. And next time I'll do a better video, or we'll see anyway. Why am I using this plate with a hole? Because this example is classic, and I know exactly what is the influence of the mesh size on the results. So maybe later on I will use my own mesh set that I created to, I don't know, to use it as an input for some FEA solver to have a look at the results. Why not? So, but for the moment, we'll look only at the meshing. So let's start. So to understand what is a mesh set, the first thing obviously is to create a mesh set and to have a look at the structure of the file generated and how, what is actually a mesh set composed of. So I used Salome, and I generated a geometry and I meshed it. If you don't know how to do that, I have plenty of videos on the channel showing you how to mesh this kind of plates. So that's not the point here. And what I'll do is that I will export this into, let's say I have available a certain number of formats here. So let's be crazy. Let's export at all of those formats, and let's have a look at what we have at the exit. So here's what I got. I got a lot of files. Some of them seems like I cannot open them. Some of them I can open them. So let's start with the DAT file. Well, because DAT is simply text file. So you see that automatically Emacs recognizes that it can open this file. So I'll just open this one and have a look at what is inside. And well, what you see is that the first line of this, there's basically two numbers. And after that, I have a list of things. So the first list here is obviously the list of the vertices of my mesh set. And you see that I have 103 of them. And then I have another list which start with another number and which is followed by 3 other numbers. And this is the ID of the vertices listed here. So this is the list of the elements which are basically stored with the ID of those vertices. So, and there's nothing more in this file, right? It's very simple. So, and that's all there is to this kind of text mesh file. So you see that the two numbers at the top are just the number of vertices and the number of elements. Now, not all the mesh formats are that simple because, engineers who build those formats, they want to save different kind of things into it in different kind of ways. Let's have a look at, I don't know, STL. So to open that, so if I think in Windows now there is a reader of STL files. So if I double click on it, I think this will be open with the Windows reader, which is actually able to kind of look at that. So it's not very pretty, but at least I'm getting something. So yeah, let's have a look rather at the text files. So let's open that with Notepad++. And you see that the format is kind of slightly more complicated, but nothing very much. So this time it saves vertices, and we have faces and normals to the faces. So we have more complex information here. And let's go down just to see what I have. And well, this is basically it. This is how STL is saving files. Now, you can't open all of those formats because some of them, like the met file, are, I think, binary formats. So if I try to open that with, yeah, I'll get this, which is basically a bunch of, I cannot read that. So, but all the other formats should be able to open them. Okay, but that's not the most important point about here, is that finally, what is a mesh set? It's a mesh set is just a bunch of nodes and a bunch of elements. So if I can generate nodes and elements with Python in Jupyter Notebook, I'll be close to generating my own mesh in a text file. So let's start and let's try to do that. So let's start by going into my folder and opening PowerShell window, and I will input Jupyter Notebook like that. So I have Jupyter Notebook installed. By the way, if you want to know more about Python or Jupyter Notebook and how to use all of that, well, you're welcome to join my Python course. So if you're in the newsletter of my blog, you will have the information about it. So, or just let me know, send me an email. Okay, so let's create a new blank canvas. What's called notebook, and let's call that simple mesh. Okay, and where to start? So starting with a blank notebook is always difficult. So what I'll do is that I'll put a photo of my plate with a hole in it. So I have this photo here that I just placed into my folder. And what I'll do is that I will transform this cell into markdown cell. So that's basically, I can write some stuff. So basically some text to describe what I'll be doing. And I will use a magic method. So it's because there is this sign at the beginning. And I will basically, if I run this node, you see that the image of my plate just appears here. So that's pretty nice. So now I have some inspiration to work with my geometry. So if I think about what I need to do to complete what I want to do, and I write that into steps because it will help me to create an algorithm to do this. The first step will be create nodes. So I want to create nodes which are within this plate geometry. Second will be create elements. So I'll have to kind of link those nodes to create elements. And third will be export into a file, right? So this is generally the structure of my algorithm. That's what I want to do. So the first step, node. How do I create nodes? And one of the critical stuff is that, well, I can create nodes, right? But how do I know they are at the position I want? I need some way basically to display those nodes. So the first step really into my my algorithm will be to create nodes and then display those nodes. So let's put that as 1, 1, and then we'll have 1, 2 display nodes, right? So this, I will just take it out and maybe put it into another node that I'll think about it later when I will come to this stage. And now my first step will be create a node. So the first thing I can do is, what will be the structure of my node? So let's create manually a few nodes just like that. So let's put that into an array. So let's say I want 0, 1. So I will work in 2D, right? So 0, 1, 0. Maybe the first one should be 0, 0, right? 0, 1, 1, 0, and 1, 1. I think nothing more simple than that. That's my node, right? So how do I, so I can calculate this, but I don't see anything. But if I want to see the result, I can put this variable here, and my array of 4 nodes or vertices is now created. How do I display this? Well, to display that, I will use matplotlib. So the first step before this should be to import it. So and at the same time, I know that I will need NumPy and I will need some math functions. So I'm just importing those 3 Python modules, NumPy, matplotlib, and math. And now to display the nodes, well, I'll use plt.plot. And now what I need to give it is nodes, and I need to separate the first indices from the second indices and to pass that separately to the PLT plot in order to plot it. So to do this, there is a useful method like this. If you put this sign and 0, this will automatically extract. So we can, by the way, can have a look just so you understand what I'm doing here. Oh yeah, okay, I forgot. I have to make that a NumPy array, because now it's just a simple Python list. So let's calculate the cell. Yeah, and now you see that it automatically extracted the first range, the x indices of the nodes, right? And if I put 1 here, it extracted the second indices. So if I use plt plot nodes 1, and in the second time I use this, and I want to plot that as a small O sign, and now I have to do plt.show. Let's try that. And it's cool, seems to be working. So now I have my 4 nodes plotted into a graph. Let's separate that and put that into this node here. That will be more convenient, right? So now that I created manually those 4 nodes, what I have to do is to find a way to create nodes within this plate shape, right? How do I create the nodes within this plate shape to basically generate my set of nodes? So let's start with the dimension of the rectangle, and then I'll think about the circle part after that. So I will need the dimension. So let's create a few variables. L will be equal to 0.1. Let's put all the units in meter. 0.1. H will be equal to 0.05. R will be equal to 0.02. And yeah, so now that I have this, what I want to do is basically let's hide this. I don't need it anymore. Instead, I'll create a set of nodes which has nothing inside. So it will just be like this. And maybe let's make it right away an NP array like that. Okay, so and now I have to add the nodes within this array. So the way to do this, I think, could be a for loop. So for x in and in Python, so you could use in range something, so in range of L. But there's a problem here as this function range only take an integer as the variable here. So I cannot use this, I will get an error. And that's where NumPy has a very useful function called linspace. So if you look at this, so this is a NumPy documentation, you have this linspace function, which basically is exactly what I have. You start value, end value, and the number of elements I want. So I'll need a variable, an additional variable, which is nb element, and let's put that as, I don't know, 10 to start with. And so in range, let's use this np.linspace, and so let's start from 0 and let's go up to L, and let's use nb element as the number of elements. And I want to generate both x and y value, so this will be a nested loop. So I'm basically just copying that and pasting this here. Instead of x, I replace with y, and this will be h. I will use the same number of elements. And for each of them, I will, let's say, append my node x and y into the. So first, let's run that just to see if I didn't do any mistake, and I did. Okay, so seems like I cannot. Okay, I cannot append like that into an NP array. So let's, for the moment, so I'll convert that afterwards to NP array, but for the moment, I'll just use a simple Python list. Okay, now it seems to be working. How do I know if I'm actually putting the right elements into it? Well, let's first, let's have a look. So it seems to have what I want, some coordinates here. That's good. So let's run this. Okay, so now it must be an NP array to have that. So what I'll do is that here I'll do a conversion. So I'll call that points, and this will be equal to np dot array of my nodes. And yeah, of course, here I have to replace that with points. Okay, so that seems to have worked, at least in some way. So I have discretized as domain, which is for the moment just a square. Now the kind of complex part is, how do I take account of this circle here? And again, here I'm just putting in my own basic thinking. I do not have that much experience in this kind of problem, so I'll do something pretty basic. And if you have some experience about, or idea of how to generate that better, just let me know in the comments. I'm, happy to hear about what you think and eventually improve this later on. So the kind of primitive way I'm gonna do this is, so it's just by doing the exact same way, but in taking into account that I have the circle here. So just think about, if you do what I'm doing here, I'm going from the x0 to the L value. At one moment, the x will be within this part of the circle that I don't want, and at one part, it will be in this part which I want. So the y, when x is here, I do not want x value, and I want the y to be on the circle, basically, to start on the circle. So how do I do that? Well, my idea is to introduce an if condition, which will basically say, So if my x is inferior to r, which is the ray of the circle, then, so yeah, and this has to go after that. So I will sum up the y value after going into this loop. So if my x is inferior to that, my y should start on the circle. So how do I know it will start on the circle? Well, I have to give it a y0 value, which will be on the circle. So how do I know the y0 is on the circle? Well, I know the x value, right? I know the ray of the circle. So I can take basically the root of my like that. So I have a circle equation, which is x squared plus y squared equal the ray square, right? So if I want this y value when this x is here, it should start here basically. And okay, and and because it should start at y0, the value here should be y0, and this, make sure the indentation of your script is correct. Then this will append the node xy here. So now the second condition, if x is not inferior to y, so else I'll do the exact same thing, but I will start at 0. Okay, and I will still append the nodes. So let's see if this works or not. Let's see what I have now. Cool. So seems to be working in some way. So at least I get this. The nodes are not within the circle here. So again, I'm not sure this is the best way to do it. This is just a way I found. So I'm pretty sure that you could find another way to sample this plate. Let's have some fun. Let's try to change the number of elements to 20. And indeed, the kind of the mesh accuracy, well, it's not mesh, the vertices are taking more and more the shape of a plate. Okay, so I think I have my first step in my algorithm, the generation of the nodes. Now let's think about the second step, the creation of elements. So let's think one close second about how to create elements and what kind of elements I want. Because of course, the first thing to think about is the type of elements. So I'll use triangular elements for that because this is the most common type of elements used in FEA. And what is a triangular element? It's basically a set of 3 vertices or 3 nodes. So I had to find a way to group all those nodes together to creating a set of triangle elements. And then I'll get my mesh. So I will not reinvent the wheel here. Generally, there is something called triangulation, which starts with a point cloud and will generate for you elements. And one of the most simple, well, not simple, one of the methods which is usually used and which actually is one of the key methods in the meshing algorithms is the Delaunay triangulation. So Delaunay triangulation is what basically creates the mesh sets. So if you have time, you can read this Wikipedia article, very interesting, and it shows you how it works, how it starts with some point and calculate the distance between the nodes and, and then create the mesh. Now, because we are in Python and there are already a lot of modules available. Well, I won't reinvent this Delaunay algorithm because it's way too complicated. So I'll just have a look at Google and what module I can use for that. And in the SciPy library, there is the Delaunay algorithm, which is actually already available. So that's awesome. So if you see here, you have an example. All you have to do is to import this, scipy.special import Delaunay. Then you pass your points to the Delaunay algorithm and it generates a set of points. And then you can plot that using matplotlib again. So let's have a look at this. Let's copy this here into my, like that. Let's see if that works, because that seems to be working, right? Cool. Let's have look at what is inside, no, not this, inside this. Okay, so seems like I'm not able to see this object. So we can plot it. Okay, so that's how you actually plot it. And it uses this plt.treeplot. Okay, this, and so let's paste that here. Let's have a look. Oh, that's cool. So it looks pretty much like I want. And it looks like I can access the content of my tree using this tree.simplices. So let's just have a look at what is inside this object. And it looks like mesh elements, right? This is IDs of my vertices kind of sorted in a certain way. That's very cool. Now this is not exactly what I want because, well, it's not very much good quality. So maybe there's an option somewhere, but you can see here, there's a big element here on the whole. So the quality of this whole here is a bit not that good like I want. So I thought a long time about how to actually do this. And what I came up with was, why not remove those elements that I don't want on this sides using some kind of way. And then I will have my mesh sets. So this is what I came up with. So my idea is to create a set of points on a circle of, slightly smaller than the actual ray of this circle. So 0.0195, and I'll create a set of points, well, a list of points, which will be on that circle. And then I'm using a function to find the elements which contain those points. So if you go on this Delaunay, you see that it has a certain number of functions at the bottom that you can use. And this one, for example, find simplex, which will find the simplices containing the given points. So what they call simplices here is basically the element. So if I execute this, I'm getting an array of elements. So -1 means that there's no element in it. And the rest of those are the ID of the elements that are intersecting with my sub-circle here. So now the only thing I have to do is to remove those elements from my mesh sets. And it seems that NumPy has a delete method that I can use to remove elements from an array. So you basically give it np.delete, you give it the array, you give it a set of IDs that you want to remove from the array, and at the end you pass one value, either 0 or 1. So not, let's see this. Yeah, so this is to copy the array. Okay, so let's try that. Let's create a new. And so my array is 3.simplices. The IDs I want to remove are 153, 154, 21, and 0. And I'll put all of this into a new mesh set called mesh. So let's run this, see if it works. So now I have no idea to know if this worked. So let's basically plot again. And instead of 3.simplices, I replace that with mesh. Oh, seems to be working, as you can see in this mesh array. Now I have a much better curvature here. I do not have those elements. Now, of course, you know, as an FEA engineer, what you will think is that, okay, yeah, you got a mesh set, but the aspect ratio of those triangles here are very bad. Well, one way to solve that would be to get much more elements here around the circle, or to get a different way to sample this, or maybe to split that into several domains. Well, there are a lot of ways, and if you want to give it a try, please be my guest. Have a try at making a better mesh, and let me know how you did, and I'll do an update to the video, or I do a second video with your solution. But for the time being, this is what I got. This is my mesh set, and I've almost won. The last step is to export that into a file. So let's start by creating a file, and let's give it a name. Let's call it plate mesh, and I'll give it the DAT extension. Well, I could call it like I want, txt or anything. This will be a text file anyway. And this will be open into write mode, so W. And let's test if this works by writing something into it. So let's write, I don't know, 0, 1, 2, like that as a string. And let's close the file. That's the basic code to generate a file. Let's run that. So if you remember, the file starts with the number of nodes, NB nodes. And how do I know number of nodes? I can calculate that using the len function of my my points mesh set, like this. So let's have a look at 400 nodes. Okay, so that's the first parameter. The second will be the number of element. This will be the len of my mesh. Okay, now how do I write that in the format I want into my text file? Well, I'll basically use a for loop. So for node in nodes, and now I could let's have a go at printing maybe printing with format like this, dot format, and the first thing I want to print is the coordinate 0 of the node and the coordinate 1 on the node. So if I do this, I'm getting basically a list of the first and the second coordinate, so that's what I wanted. But there's just one more thing, is if you remember the formats, the first column should be the number of node, the ID of this node. So how do I know that? Because it's not included into the nodes file. Well, there is a useful function in Python called enumerate. So if you add I and a point like this, a comma, in enumerate nodes, this will automatically create the indices you need. So I'll like that, and add the I variable in the format. And if I execute now, I am getting exactly the format I wanted for this. So let's start by writing this to my file. So instead of print, I will do a file.write here. I will remove this. And if you remember, the first line of this should be the number of elements and the number of nodes. So this too. Number of elements. Cool. So let's have a look. Let's try that. So it was executed. So let's have a look at what I'm getting. So my file now is 16 kilobytes. So I have more data into it, which is a good sign. And yeah, so I'm getting this. So not exactly what I want, because I want it to be written in the actual format. And so how can I change this? Okay, maybe I guess I have to put this at the end. Oh, not here. Okay, let's run that again. Yeah, and now I'm getting the right format. Awesome. So now I just need to add the elements, and that will be a win. So let's use exactly the same strategy, and let's have a try here in this node before writing it here. So instead of I will write J. I could use I, but just for the sake of difference, I will change the index here. And instead of nodes, this time I want mesh, and I will change that to LM. So for each element into mesh, I will iterate and get element 0, 1, and there are three variable into 3 vertices per element, right? So this should be it. Let's have a look. Yeah, and I forgot to add another curly braces here. And yeah, I'm basically getting what I want. So let's just put this loop here. Let's run that. And oh, sorry, I should replace that by the print should be replaced by file.write. Let's write this, and now I should have my mesh file. So now it is 28 kilobytes, so there's more information into this file. And now I have the element, and if I go down, I have the mesh, the nodes and the mesh. So this is particularly identical to what I would get with Salome generating the .dat text file. And that's basically it for this video. So the purpose was just to have a fun learning project together to see how to generate nodes and to generate elements, and to have a bit better understanding about mesh in general, and how the mesh structure works. So I guess it can be improved, of course, and if you have some ideas, just let me know. And then we can use that as the input for, I don't know, our own small FEA solver in Jupyter Notebook, maybe. So I'll have a think about how to continue this little project, and if you like this kind of thing, just let me know. And don't forget to give it a like, subscribe to my channel if you think this is useful. And as usual, thank you very much for watching my videos. You're the best.